Section 16.4.3 Maximum Order. Sandra's objective in all of this is to make the family F as large as possible so that she and Riva have lots of choices for their matrices S and R. A useful trick is to watch the multiplicative orders for differences in the sets of factors. For example, if the multiplicative order of A is 19m and the multiplicative order of B is 23m, then the multiplicative order of AB just might be 19 times 23m equals 437m. If that doesn't work, then A prime, B, or AB prime may have multiplicative order 437m. If at all possible, Sandra should choose a generating matrix F whose multiplicative order has a large prime factor, say m larger than 10 to the power 35, in order to prevent a Silver-Polig-Hellman attack, section 14.4. Sandra will need to factor 2 to the power n minus 1 for various n to find the ones that have large prime factors, and then find a generating matrix whose multiplicative order is divisible by one of those 2 to the power n minus 1 by trying successively larger matrices. Section 16.4.4 Emily Attacks. Suppose that Sandra has chosen F and the family F and that she has sent a message to Riva. Since Sandra and Riva are communicating over a public channel such as the Internet, assume that Emily knows F family F, SM, RSM, and RM. Her goal is to find either R or S, so she gets 2 chances. Let's concentrate on how Emily might find R. Emily knows 2 things about R. First, she knows the values of SM and RSM, so that gives her a set of n linear equations in the n to the power 2 unknown elements of R. Second, she knows that R is in the family F, so it must commute with F, namely RF equals FR. If the ring R is commutative, then this gives her n brackets n minus 1 additional linear equations in the n to the power 2 elements of R. This works because the left side of the matrix equation RF equals FR produces sums of terms of the form RF, where R is an unknown element of R and F is a known element of F. The right side produces terms of the form FR. Since the ring is commutative, the left side terms RF can be converted to the form FR and combined with the right side terms to form linear equations. With n to the power 2 linear equations in n to the power 2 unknowns, it would seem like child's play to solve those linear equations and find R. It's not that easy. Recall from section 15.3.1 that there are strong congruences and weak congruences. The same is true for linear equations over any finite ring whose size is not a prime. The more prime factors the ring size has, the more potential for weak equations. In the present case, the ring size is 2 to the power 8 with 8 prime factors, so many of the linear equations are likely to be weak. A typical size for the matrices might be 30 by 30 if the ring R were well chosen, or 128 by 128, or even 256 by 256 with a poor choice of ring. Even with a well-chosen ring, and even if half of the equations are strong, you would expect to have at least 2 to the power 450 solutions to the set of 30 times 30 equals 900 equations. In practice, the number of solutions is much greater because there can be equations with 4, 8, or possibly 16 solutions. There is good news for Emily. Emily can solve for R prime instead of R, and whichever one of those 2 to the power 450 or more solutions she gets will be a valid inverse of R, letting her obtain the message by R prime Rm equals M. Section 16.4.5 Non-commutative ring. It looks like Sandra and Riva are sunk. Emily has won this battle. One possible answer to this attack would be for Sandra and Riva to use a non-commutative ring. Two examples of non-commutative rings are matrices and quaternions, section 15.7.2. You can form matrices whose elements are themselves matrices or quaternions, or, conversely, quaternions whose coefficients are matrices or quaternions. None of these are good choices. You would need to make them very large to produce matrices of high multiplicative order. A better route is to construct your own ring N using the techniques of section 15.7. You should choose a ring that has many elements that 1. Are invertible, 2. Have high multiplicative order, and 3. Are non-commutative. It is a tricky balancing act to find a ring that has all of these features. For example, a ring that has elements of maximal multiplicative order, 255 for a 256 element ring, could not have any non-commutative elements. If you could find a ring where half of the elements are invertible, half have multiplicative order equal to about half the ring size, and half are non-commutative, dayenu, it would be sufficient. You cannot achieve all three of these goals simultaneously, but you may exceed some while coming close on the others. With a non-commutative ring, the matrix equation Rf equals Fr can no longer be linearized because it is no longer certain that Rf equals Fr. Instead, the matrix equation leads to a set of bilinear equations. The general term in a bilinear equation takes the form AXB, where A and B are elements of the ring, and X is a variable whose value you wish to determine. While linear equations can be solved using a simple systematic approach, namely Gaussian elimination, there is no such method for bilinear equations. There is not even a general method for solving such a simple equation as AX plus XB equals C with a single variable X, so solving bilinear equations over a ring is impossible.